All right, recording is rolling. Welcome to Monday, November 15th. You guys just turned in your Open Notes Take Home Momentum quiz, so thank you for doing that. And you know what? I'm telling you guys and honors are really similar stories. So let's take a look at well, I'll show for both. Right. So you guys, AP Physics have a new homework page clipped to the front of your desk. Looks like this says Chapter 8. Right. And I've got main homework problems for you guys and some bonus problems. Also, you guys have an AP Classroom Unit 7 multiple choice that, well, none of this is going to be due for quite a while because we have a whole Thanksgiving week break coming up so pretty soon. Right now, for my honors classes, I'm going to see if I can fit this all in one video here. Uh, my honors classes have also Chapter 8, just from a different book. That looks like this. Okay, and got your homework puzzles here and your bonus problems there. There you go. Right. Okay, but you guys, AP, see it this way. Okay. So we're going back to rotation stuff. Now I know in the past we've done some rotation stuff by AP's book. It's Unit 3, but then Unit 7 is rotational dynamics. So we're going to go back to that. Right, so over the next few days, here's the topics that we're going to be going over. This is outlined for the adventure we're going on. Now these first 2 points we've talked about in the past. We've touched on kinematic motion and we've done a whole section on centripetal force, so I'll recap those for you guys. Right. Then, close to the end of class today, I'll start talking about rotational inertia and then start setting up torque. Okay. And then we'll hit these topics later on. So these bottom 4 bullet points are going to be completely fresh new material. Right. Then Thursday, Friday, my plan is to set you guys up with a fun project. So that's the plan. All right, you guys ready to get going? Right. So let's talk about a kinematic motion first. Now, you guys remember in a linear context, you guys remember these 3 kinematic formulas right, that are probably a good idea to memorize? Okay. Well, there's rotational equivalents of those. Let's think, how could you measure something in a rotational context and make sense of this? Okay. So you guys see this Roosevelt right here? Okay. Give this turntable a spin. Yeah, turntable's back. Okay. And maybe I want to quantify something about that motion that you just saw, something like that. So what could I say about that motion? Okay. Well, I could say, hey, maybe how far has this Roosevelt moved in some number of centimeters or some number of meters, right? But maybe since this is a turntable, I actually want to know how far this thing is spun. And maybe those two are related to each other. And maybe it has something to do with this radial distance too, right? Look at that. Right? All those points have the same turns per time, but they have different linear speeds if I point a motion detector at each of those, right? So how's this go? Well, how, here, see this way, right? 1 revolution, right? That's one way you can measure like 1 complete turn, 1 revolution. Right? That's also called how many degrees? 360 degrees, right? And revolutions is pretty intuitive. You guys have grown up using degrees, but probably just in high school, you guys learned a 3rd way to measure how far something's turned, which is what? Radian. Yeah, nope, I heard 2 pi also. 2 pi radians. Yeah. And radians turns out is actually the best way to measure angles because this is the only angle measurement that you can plug directly into equations. If you paid real close attention, anytime there were some number of degrees involved in something, it's always inside a sine or a cosine in the calculator. But you can never just multiply an angle straight by something. Right? But you can if you're working with radians. Right? So how far has that Roosevelt walked around and say some number of meters? Right? Well, that's related to how far it's turned around in radians. You just multiply by the radial distance from the center, say in some number of like meters, something like that. Okay, and right there, you're already seeing one application of that. Okay, the fact that you want to use radians to measure how far around. Oh, by the way, you guys are going to see a lot of symbols today that you have seen before, so I'm not going to take time to spell out. But you guys know that theta represents angular displacement, not the radians. This is just review. But if you need a page to refer to, you guys remember this page that you picked up on the very first day that you guys walked in here in August? Right, so we're doing all this rotational stuff, and Here's the variables, here's what they stand for, here's the units they're measured in, some notes, right? So if you need that page. Yeah. Okay, how far there's also how fast in meters per second. And there could all, no, that's if you point a motion detector at it, right? Radar gun. Right? There's also how fast is this thing spinning? Right? Like you guys know the Earth spins one revolution every 24 hours, and that's called, what's that called again? Like the spin rate? It's the technical term for spin rate. It's like angular velocity, and it's represented with Greek letter omega. So omega and radians per second, yeah, multiplied by also distance from the center. Okay, so we got x, we got v. The next one that logically follows is a, acceleration, meters per second squared. Right? Suppose this turntable is speeding up spinning or slowing down spinning. See there, see it slowing to a stop. Right? Well, that'd be alpha, like radians per second squared. How quickly is it speeding up or slowing down spinning times radial distance from the center, some number of meters. Is that right? You guys remember this? Right? So that's how you convert back and forth between how fast something's spinning and how fast is it moving in a linear context, right? Just multiply or divide by this radial distance from the center, depending on which way you're going. Okay. Should do it this way, starting from the center, 0 moving out. Okay. All right. Do you guys remember 1 radian? Approximately how many degrees that's equal to? Yeah, it is about 57 degrees. You guys remember that? Because, yes, if you take 360 degrees and divide by the 2 pi radians, you get, 57.2957. Okay, so 57 degrees is pretty close to 1 radian. If you're ever wondering, what the heck is a radian? It's a little short of 60 degrees. Okay. Set you guys up with, here, draw this turntable. Okay. There's, say, for example, if there's some radial distance r, park this coin right on the edge. Okay? And what if I took this distance r as a piece of string, and it took that string and just wrapped it around? It'd probably make it to about that far, right? And that would be 1 radian, about 57 degrees. Okay? So that's what 1 radian is. Okay? Oh, and it takes 2 pi of those to make it all the way around. In fact, you guys see this right here, x equals theta r? This is a general version of probably a specific formula you guys have known since elementary school, which is circumference equals 2 pi r. Where 2 pi is exactly 1 trip around the circle, right? In terms of radians, circumference equals 2 pi r, right? So this is some theta, this is some x, and could be circumference if it's all the way around. Okay. Now, what formulas are going to tie these variables together? Well, there's 3 kinematic variable formulas, but just pop in the rotational equivalents for the variables. So I got, instead of x, it's theta. So theta equals omega naught t plus half alpha t squared. Got your omega final is equal to omega initial plus alpha t. And you got your omega final squared is equal to omega initial squared plus 2 alpha theta. Right? So the analogous parts are x equals v naught t plus half at squared. V final equals v initial plus at. And v final squared equals v initial squared plus 2ax. Right? Okay. So these 3 kinematic formulas right here. Right? And that's that yellow poster up above. Yeah. Yeah. Right. So, okay. So let's solve a problem with this. So this is review. You guys have sort of seen this before. Touch on this. Let's do an example. Say I got this coin, okay, and I'm going to get this a spin, and we're going to make some measurement. Just kind of ballpark some measurements. Okay? We make a tax VV checklist, except it's going to go T alpha theta omega naught omega final. Right? That's the rotational equivalence of tax VV, right? So you got seconds, radians per second per passing second, radians, then radians per second on each of these. Okay, like that. Okay. How many variables do I have to have measured values for before I can make any kind of calculation? Yeah, 3. As long as you know 3 things, then everything else is determinable, right? So I'll give this thing a spin. Count, tick, tick, tick. Right, and let's say it slows to a stop there, right? I'm sort of fudging stuff a little bit because I found some I stumbled across some pretty good numbers earlier today. Okay. Suppose this turned from here all the way to there and then came to a stop, something like that. Okay. So I know that 1 revolution is 2 pi radians. It went a little bit beyond that. 2 pi is not like 6.28. Right? So a little bit beyond that, maybe I'll round that to about 7 radians. 7 radians. Okay. Okay. And let's say I timed that, and that whole thing took 2 seconds exactly, and it came to a stop. Okay. Well, that's only 2 values. Wait, do you know the third value? If it came to a stop? What else do you know? Final omega. Omega final is equal to 0, because that's coming to a stop, isn't it? Okay, so now I know 3 things. I got 2 seconds it took to turn 7 radians, so a little bit more than a revolution, to come to rest. 0 radians per second. Okay. Okay. There is enough information lying around that, in principle, you could solve for how fast did I kickstart this thing to begin with. We're assuming that it slowed down at a uniform rate. And then what is that uniform rate that it slowed down? Okay. Okay. So can you figure out those 2 things? Okay. Now, that's probably the easiest go-to example, just to throw something on a page, just live demo, turntable, blah, blah, just those numbers. But I'll tell you what else too, is that this is the most difficult problem to solve in terms of starting information, right? Because if you, here, I'll show you guys exactly why. You guys know we're going to use these formulas to solve it, right? Okay. What do we not know? We don't know alpha or omega naught. Here's alpha, omega naught. Okay, so that one can't get it by itself because there would be 2 unknowns. But there are also the same 2 unknowns in this one, alpha and omega naught. And also here, alpha and omega naught. Do you guys see that? You guys probably remember this from linear motion too, right? Anytime you know these 3, that's the most difficult one to solve, right? So we can't solve this with the system of equations, and that's what we're going to do. I'll tell you what else too. You could probably solve this a bit faster with a graph. So after we solve this with system of equations, I'll show you guys the graphical approach, which is probably a little bit faster. Okay. So I'm just going to take these top 2 and make system of equations out of those. Okay. So theta, which was 7 radians. Follow my notes, make sure. Yeah, here. 7 radians that it turned is equal to, well, I don't know what omega naught was. I don't know how fast it was spinning to start off with. Okay. But I know that this whole process came to stop in 2 seconds. And then plus 1/2 times alpha, we don't know yet. That's the rate it's slowing down. I bet alpha is a negative number, so slowing down. And then 2 seconds being squared, like that. Okay, so 2 unknowns. How about the second formula? Turn that into an equation. Omega final, 0 radians per second, from omega initial, which we don't know yet, plus alpha, which we also don't know, times the 2 second time interval to come to a stop. Okay. Here is your system of equations. Right. Now, if you can figure out, if you can get that far, then you know enough physics to do the setup. So the rest of this process is just going to be math, right? So think back to math class. How do you solve system of equations? There's multiple ways. See if you guys can beat me to the answer. Here's what I'm going to do. My process is going to be, I'm going to take this bottom one, solve for alpha in terms of omega, and substitute that into the top one, and then figure it out from there. So rearrange this. It looks like alpha is equal to negative omega naught divided by 2 seconds. Okay. So this is what I'm going to substitute this expression right here for alpha. Okay. Then take this top formula, sub this in. I got 7 radians is equal to omega naught times 2 seconds, okay, plus 1/2. Okay, now here's where the substitution comes in play. Instead of saying alpha, I'm going to say negative omega naught divided by 2 seconds. Okay, all times 2 seconds being squared. Okay. Like that. Okay. Now I can solve this because there's only one unknown in this equation. I mean, that's the point of the substitution. Right, so this 2 seconds and this 2 seconds is going to cancel. Now, just as it happens, this 2 and this 2 also cancel, and I still have the seconds though. Right? So I got 2 omega naught minus omega naught, does that just leave me with plain omega naught? Okay. 2 of something minus 1 of something. Okay. So I'm looking at omega naught is equal to, and then I have to divide both sides by seconds. Okay. It'd be 7 radians divided by 1 second, be 7 radians per second. Okay. That's how fast this turntable was spinning at the start of that interval. I gave it a kick of 7 radians per second and slowed to a stop in 2 seconds. Okay. So go back to my checklist. We just checked this box right here. This happened to be 7 radians per second for all this to play out. Okay. But I want to know one more thing. I want to know what was the rate this was slowing down, this alpha value, okay. Which as we're going through this week, this alpha could be involved in something called torque. You guys are going to see. So that could be a connection that make in the future. And so what is alpha? Well, I'm going to go back to this substitution and this answer for omega naught. Omega naught was 7 radians per second divided by 2 seconds. You guys see that alpha must be negative 7 over 2 radians per second squared. If you want it, you could even call it negative 3.5 radians per second squared. There, right? Second. Okay, so that's application of those kinematic formulas, just in a rotational context. You guys good? But I said we're also going to do a graph review. Okay. I love graphs. AP loves graphs. You see graphs all over the place. Okay. Let's turn this into a graph. Now, think back to kinematic motion. This is quite a while back now. Okay. We were looking at different kinds of graphs for kinematic motion. X versus t, v versus t, a versus t. But one of those graphs was especially information rich because you could not only get, but you could actually get all three. You could get x, v, and a information out of it. And which graph was that? Yes, the v1. Yeah, velocity versus time. Okay. So we'll do the analogous part to that, which is omega in radians per second versus time in seconds. Okay. Now, for that example I just showed you, here, do it one more time. Give this thing a spin, and it slows uniformly to a stop. Try it again. Give it a spin, and it slows uniformly to a stop. Okay. Can you guys draw the graph for that? Okay. Can you guys beat me to the graph? Draw it before I do. What does that look like? Did you guys draw, let's say, well, I know at time 0 it would have been moving, some kind of omega naught, right? And then, if it slows to a stop after some time, wouldn't have to do that. Is that true? Okay. And then for AP1, you always assume that it's just basically a straight line. Okay. Some weird exceptions to that, but all right. Let's apply the numbers that we got, because and then forgot to fill this in. This is negative 3.5 radians per second squared. Right. Let's see how these numbers match with this graph. Okay. So this whole thing happened in 2 seconds. So I'm going to put 2 seconds right here. Okay. Omega naught was, we calculated that to be 7 radians per second. So this is sort of working back from the solution, although it could work the other way too. This is 7 radians per second. Actually, sort of being redundant with those units because they're already specified in the axes, right? What property of that graph tells you alpha? The slope. Good call. Hey, wouldn't that just be rise over run? Rise over run. I see down 7 over 2. Oh, that's exactly negative 3.5 radians per second squared. Okay. So alpha is negative 3.5 radians per second squared. Okay. And what property of that graph tells you how far this whole thing's turned? The area. The area under the graph. Yeah, area under the curve. So you'll stick with this kind of red ink, burgundy red. So this right here tells you theta. Okay. Okay, so shouldn't that just be the area of that triangle? 1/2 base height, right? 1/2 times the base of 2 seconds times a height of 7 radians per second. the second, that second's going to cancel. The 2 and the 1/2 cancels. And look at 7 radians. 7 radians. Oh, which is exactly the starting value that I was using to measure. Said, rotate about 7 radians. Okay, so again, the graph sort of worked backwards from the answer, but yeah, guess that. See how the equations, the graph all line up? Okay. All right, so that is our review of kinematic motion. Let's go. You guys got any questions? Okay, let's look at the other topic that you guys have already seen before also. Do a quick review, which is centripetal force. Because I might ask another question about this coin. I might want to know what's the force that's, what's the magnitude of the force that's holding it in a circle as it's going around the circle. So centripetal force. Okay. Now remember that centripetal force is never a force unto itself. It's always a force that's provided by one of your classic forces. Okay. In this case, what force is actually holding the coin on the turntable? Friction. Friction, right? So this could totally be an AP question. But I really expect this to show up, right? They might say, like, what force is acting as a centripetal force, or some version of that. You say, well, this case would be friction, but what are other options? Could be tension in the string, could be like gravitational force if it's holding a satellite in orbit, could be some component of a normal force, say a car's on a banked wall, right? That's one of your classic forces. Right? And you guys know a formula for centripetal force. So you might know a couple of them. Right? And not necessarily because I gave it to you, you got it out of a book, but because you guys did a whole lab on this. You guys remember taking the PVC pipe, Play-Doh canister? There was some swinging mass, some radial size of this loop. And this was being held in check by some weight that I'll label F like a force, like a weight. Right? And, oh, one more thing. You guys know the speed as it's going around, V. Right? All right, what formula links those 4 variables? Exactly, mv squared on r. Yeah, that's a good one to know right there, mv squared on r. Okay. How about on the AP equation page? I mean, it's good to be familiar with where these equations are here, right? Well, they don't exactly give it to you, but they give you one that's adjacent to it, which is centripetal acceleration. It sees v squared over r. But, you know, that's just Newton's second law of motion away from that, right? Just multiply that now so you get back to force, right? All that stuff, right? Okay. But you know what? This is in terms of linear velocity v, and already, thinking rotationally, you know, there's another kind of velocity called omega, which is like a spin rate, right? Like angular velocity, radians per second, which might be useful for maybe like a turntable, or usually like any solid disk that's all turning together. Okay. So do you guys remember the formula for that? Or for centripetal force in terms of omega? How about this? Okay. Back near the beginning of class, remember look at this right here. You guys remember how to convert between linear velocity and angular velocity? You either multiply or divide by radius, depending on which way you're going. Right? Hey, can we substitute that in there? Centripetal force is equal to m times, not v, but omega times r. Squared divided by r. See, I just did a little substitution. Just took that, substitute it right there. And then, let's see, omega would be squared. R would also be squared, but it cancels, one of them cancels out. Okay. And you end up with this expression right here. M times omega squared times R. Okay. So that's the other perspective on centripetal force.
Wait, so why is it omega R?
Okay, yeah. Why is it omega R? Because if you want to know, here, so this goes back to beginning class today. Right? If you want to know, say, give this turntable a spin, and I want to know what's the speed of this coin moving around, right? Say I point a motion detector at it, or a radar gun at it, or maybe I assume like this is a little vehicle on a circular track. I want to know what's the speedometer reading. Right? Any of those stories that you want to attach to it. Right? Well, if you know the rate that he's spinning around, like radians per second, right? How fast is this whole turntable spinning, and you multiply that by the distance from the center, in this case, looks like about 12 centimeters. You see 12 centimeters? Okay. Then that's how you get to V.
Okay.
Right? Yeah, so that's the substitution I made here. Is instead of V, now it's just going to be omega R. And then just check it through the formula and you get that new expression. All right, so you guys seen this before. In fact, this Thursday, Friday, I'm going to set you guys up with the O'Neill cylinder project. You guys remember O'Neill cylinder? Okay. Yeah, so that's going to come back. This big old cylinder rotating in space about this axis. Okay. And I wonder if how fast you have to get this thing to spin so that like somebody at the surface feels like they have artificial gravity, all that stuff. Well, divide by mass. Something to do with omega squared r. You want omega squared r to be 9.8 meters per second squared. Okay. All that. Okay. How fast is this thing spinning? Okay. Okay. So I want to say on that. Oh, no. I wanted to talk about this coin. So I wonder, what is the centripetal force? Say, oh, no, you guys told me it would be specifically provided by the friction. So what is the friction force that's holding this coin in a circle? Okay. Well, let's play off this one. So omega, we figured out was, oh, no, it would be changing because, of course, it's slowing down. But let's say the initial kick, when they initially started it, okay, because, of course, it eventually dissipated to zero. Okay. But right at the beginning, remember how right at the beginning, it was going 7 radians per second? So we got our 7 radians per second. You guys saw 12 centimeters from the edge. The last bit of info you'd have to know for friction force would be the mass of the coin, which is 2.27 grams. So, I ran out of paper, didn't I? Okay. Next page, I guess. Okay. So, playing off this one right here, the centripetal force would be your, what did you say, 2.27 grams? Okay. 2.27 grams, that you guys know, divide by 1,000 grams per kilogram, because I want everything in base SI units, okay, times omega squared. Now, omega was, what's that, 7 radians per second? 7 radians per second, okay, being squared, all times the radial distance, which was 12 centimeters, that's 0.12 meters. Okay. So that. Okay. Let's see what the, well, I should really say frictional force. Okay. So frictional force was holding that coin on the turntable. 2.27 on 1,000 times 7 squared times 0.12. I'm looking at, whoops, wrong piece. 2.27 on 1,000 times 7 squared. Just check my stuff. Yeah, I think we're good. Okay. Looking at 0.0133. What unit is that? Kilogram, meter, second, Newton. What is that? Joules? Newtons. Yeah, Newtons. That's how you measure force. Right? That's a really tiny force. Maybe I don't even want newtons. Maybe I want millinewtons. How many millinewtons is that equal to? 13.3. There you go. Millinewtons. Okay. Because milli is 3 decimal places. Guys remember that? All right. Got that. Got that. All right. That's all review stuff. Okay, you guys ready for some new stuff? So, new concept for you guys called rotational inertia. Okay. Now, of course, we've been working with inertia for a long time in this class, going back to, by AP's book, it's Unit 2, right? So F equals ma, all that stuff. Inertia, isn't that like a property of mass, right? You guys remember, the more massive something is, if you push on it with some force, the more massive, the less it accelerates. That's Newton's second law of motion. Right? And the only inertia we've ever dealt with is just proportional to the mass. But that's true in a linear context. But now, what if something's rotating? Well, think about this. You guys see 1 kilogram right here? If I park this right on the center of the turntable and give this thing a spin, okay, so it doesn't take a lot of effort to get this thing spinning, like no problem, right? But watch what happens when, I'm not going to change the mass. All I'm going to do is change the location of this mass. Move it right out here. right? Now if I give this thing a spin, oh boy, I feel a lot more resistance to change of motion. I feel a lot more inertia. And even though we're talking about rotation stuff, this is all still consistent with linear motion, because here's why. Look at how far this moves right at the center. Hardly anywhere. Right? Look at how far this moves out on the edge. Give it the same rotational change, say like 30 degrees or something, right? Then look how far it has to move. So there'd be a lot of inertia to get it to change its state of motion, right? Something like that. So, I'm thinking that in a rotational context, the amount of inertia associated with that is not just going to be how much mass, although it's related to that too, but it's also going to be like how far from the center, right? Something to do with that too, isn't it? Right? Huh. Okay. So here, a little blip it out here. This is inertia in a rotational context. Oh, I forgot to tell you guys what letter this is. This is capital I. And any printed materials, I try to make an effort to choose some font that has serifs on it, so get those tails on there. Okay. Before I give you guys the formula for this, well, actually, I will go ahead. I'll give you guys some formulas, and then I'll give you guys some examples. Right? So for a single point, and I might be able to approximate this as a single point, get a little bit more complicated later. Okay? I'll tell you guys what it is. It's whatever mass it is times its radial distance from the center squared. So it's mr squared. You guys see what the unit for that would be, right? I got kilograms, then meter squared. So the kilogram meter squared. I see that? Okay. So that's the unit for rotational inertia, kilogram meter squared. Right? And suppose you have here, even if you look at this turntable, like what is the rotational inertia associated with this? Well, this is more like a solid disk, isn't it? Right, pretty close to. Okay. I mean, for the coin, you approximate that as a point. Just do mr squared. Do that. Okay. But what about this whole surface, right? Well, I got like a point here, a point here, a point here, a point here. There could be like a billion points. Like what's sort of like the aggregate effect? Hold on to that thought because we're going to come back to that. But in general, it'd be like you could just add up all those mr squareds, right? Say if I broke this turntable into like a billion points and I added up the mr squared of each of those billion points, I get the aggregate effect. Okay, is that true? Right. So what are some sort of like real life examples that you guys probably already know about this already? Okay. Let me give you guys 3 examples. Suppose you try to balance on your finger this pen, or like a pen or a pencil, whatever you're writing with. Can you balance that on your finger? Yes, probably pretty nearly impossible, isn't it? It's going to fall over. Okay. But watch what happens when you balance on your finger instead a meter stick. Do you think a meter stick is going to be easier or harder to balance on your finger? You guys think easier? Right. So for the camera, let me flash it. Got a meter stick right here. Okay. Show you guys live demo in class. Can you balance this on your finger? Oh man, I could just sit here all day and balance this. Okay. Now this thing wants to fall over, but it's a lot easier to keep it in place. It's almost like it has more inertia. Okay? I mean, it has a little bit more mass than the pen, sure, but probably more importantly is that its center mass is 50 centimeters up. It has like this huge radial value to its center mass versus for the pen, it's just like a few centimeters. Oh, compare this R to this R. Woo! Okay. This one is so much more radial size. You square that. Wow, it's got like a bunch of inertia in a rotational sense. So yeah, it wants to topple over, but that would be some kind of rotational motion. Okay. A lot more stable. Okay. Or how about this? What if you take this and you turn this sideways? On the honors homework, which if you're honors, watch this video, you have this, but AP, you guys have the other one. Here. In their book, there's this tightrope walker. And if you look real close, you can see he's got a big old pole, big old horizontal pole. What's that about? Well, yeah, so you got a tightrope walker. Right? See if this guy starts to topple over, then center mass gets shifted a little bit. He's just going to fall off the rope, right? Really hard to hold down. But if he's got this big old pole, think about how much more inertia that gives him in a rotational context, right? It's really hard to make that thing rotate because it's got so much mr squared. Okay? Give you guys a third example is, or I should here, second one. Here's a here's actually the first thing I should have told you guys is suppose that coin has some mass and some radial distance from the center, something like that. They'd be like just mr squared, right? Something like that. Mr squared. Okay. Here, if you guys go to a store and you walk down the bicycle row, this bicycle look like something like this. Okay. Do you guys know the most common bike tire size, like in terms of diameter? No, there are a few different ones out there, but do you guys know the most common one in the United States? 26 inches. Yeah, 26 inches. Good call. Okay. Okay, so pull out a 26-inch tire bike, ride that down the aisle a little bit. Okay. Then go pull out one that has 29-inch tires. 29-inch tires. Okay? And you will feel a difference. Which one do you think is harder to get going? 29-inch, because it has more rotational inertia, doesn't it? Okay. It's also harder to stop, so it's a lot easier with a 29-inch tire bike to like roll up on curves, like curves and stuff. Oh, yeah. Okay.
Does this have something to do with like switching gears in your bike?
Oh yeah, now switching gears is related to torque, which we're about to get into, which does also connect to this. So yeah, that there's an application of that coming up pretty soon here. Yeah, so yeah, good thought there. Okay. Now a bike tire, you guys, we can sort of simplify this a bit and say that the mass of the tire is basically all on the rim. I mean, it's pretty close to true, right? The spokes are a little bit, but okay. I wonder how much more inertia the 29-inch has compared to the 26-inch. We can do a quick calculation. Now you have to divide by 2 to convert from diameter to radius, but if we're just comparing, then that divide by 2 is going to cancel out. So also, and then that's even assuming the same mass, which even that's not true. So at least 25%, probably more rotational inertia associated with the 29-inch tires compared to the 26-inch. Yeah. You can feel that difference. Okay. Now this idea here, this inertia, this new kind of inertia, remember inertia all along in this class, we've just been looking at linear context, we've just been using mass, right? But now it's how the mass is distributed. This is going to relate to these other topics that we're doing this week. So let's see where we are in on our adventure list. Let's see, we recap this one, we recap this one. Okay, here's the one that we're on right now. This part of our story. This rotational inertia has a connection to torque, has a connection to rotational kinetic energy, has a connection to angular momentum. Yeah, this is going to come up. Okay. All right. How about this idea of, I know for a single point it's mr squared, and for a hoop like a ring, like a bike tire, couldn't you say it's this m times r squared plus this m r squared plus this m r squared, and they're all equidistant from the center, basically? So for a hoop, I bet it's also the aggregate effect is also mr squared. But what about for like a solid disk? Like I see this turntable, it's got mass here and here and here and here, and here. Like it's spread out, right? Some of the mass sure is truly on the edge, but some of it is like less than r. In fact, a lot of it has really small radial distance, right? Or what if I get the solid cylinder rolling, right? Solid cylinder rolling, if I do mr squared, well, if I take this to be the radial size of the cylinder, yeah, some of it's at the surface, but a lot of it's distributed closer to the center. Hey, what if I had a solid cylinder like this? Next to it, I have a ring that can roll, right? And let's say they're the same mass, they both like 1 kilogram. What do you think would have more associated rotational inertia? The one where, like the ring, where it's all on the edge, all mr squared, or the one where it's kind of distributed closer to the center? Which one has more inertia? Hearing a little bit of both? Right? Well, you know what? There is a table in your book with the answer. It's also one of the new posters, but the poster I printed out from the net, so it's kind of small, kind of hard to read. But every good physics textbook has a table in it of calculated rotational inertia values. So let's take a look at these. Let's see, make sure this is up, good there. Right, here, for you guys at home, just a video. You need to like screenshot this or something. This is on page 257 of College Physics. I'm also about to pull out the honors textbook too, because honors textbook is actually a little bit different. Let me zoom in so you guys can see this here. Right, so here's the ring. They start with the ring, right? Obviously, it's just MR squared because every single point is just MR squared, so that's all fine and good. Right, now let's go down. Here's the solid cylinder. We sort of cover this up. Right, now we got MR squared for every single point on the edge, but a lot of it's closer to the center, which has a radial distance less than capital R. So wouldn't have to, the aggregate effect have to be overall less than MR squared the whole thing? Right? It ends up being 1/2 MR squared. Now you can prove this with some high level calculus, but that's how it works out. So and this is one of the most common Rayleigh shapes that we're going to use in this class too, a solid cylinder. Solid cylinder rolling about this central axis, 1/2 MR squared, right? How about a bowling ball? You guys see the solid sphere here? Now I've got the answer covered up because I want you guys to think critically. Think if you can predict this before you see it, right? Solid sphere like a bowling ball. Right? What do you think has more rotational inertia? And it's not going to be a whole lot more, but slight difference between the solid cylinder and the bowling ball. Which one has more rotational inertia for equal masses? Well, which one has its mass distributed a little bit closer to the center? Yeah, I think the bowling ball is distributed a little bit closer to the center, and closer to the center is less rotational inertia, right? It ends up being 2/5. 2/5 MR squared. You guys know 2/5 is like 40%. 1/2 is 50%. So we got 0.5, 0.4, right? That's it. Right. How about a thin spherical shell? Oh, that could be like a basketball. If you guys ever see a basketball rolling down an incline, what's the inertia associated with that? Well, what do you think has more rotational inertia? A bowling ball or a basketball? Let's assume they have the same mass, which is some of these problems, mass is going to cancel out anyway. It just comes down to distribution. Right? So assuming the same mass, then which would have more rotational inertia? One where it's kind of distributed towards the center, like the bowling ball, or one where it's all at the surface, like a basketball? I'm thinking the basketball, where it's at the surface, is more spread out. It's probably closer to this very first shape, which is just pure MR squared, right? Like it has the bigger. Yep, 2/3, which is like 0.67. Yeah, it's gonna have a lot more. It's closer to this, isn't it? Okay. Then you got these other shapes. So if you have a rod that's rotating, about the center, about the endpoint, okay, you've got these different rotational inertia values. Now let me open up the honors textbook because I said I'd do that too. I'm trying to do them all in one video here. See what their table looks like. So their table does not have the basketball, but it does have a shape that you guys in college physics don't have. What's that? Nothing's broken. We're all still alive. Which is a rectangular plate about its center, something like that. And then there's a fancy formula for that. Okay, based on the length and width of that thing. Okay, and then different textbooks will have different ones. I have a poster that's pretty all-encompassing, has a bunch of shapes. Okay. I want to tell you guys one more thing about rotational inertia, which is what if you're starting from one of these shapes, but one of these shapes is like revolving around some central axis, something like that, and maybe you can't assume it away as a point mass. Right? Right. What I'm trying to get at, the idea I'm trying to get at, is something called the parallel axis theorem. Parallel axis theorem. Oh, yeah. Oh, yeah, okay. Yeah. So this is, actually, I don't know if AP even cares about this, so this is a little bit beyond the scope of like AP, but how much you guys know about this anyway? Okay. So what if you have some axis of rotation, right? And then like some object, say revolving around that. Oh, you know what I should do actually? Maybe we should do like a sphere, right? Maybe like a solid sphere. So a solid sphere would have rotational inertia of what was it? I think it was 2/5, right? 2/5 MR squared, right? Based on this R, right? So by itself, the solid sphere would be 2/5 MR squared. Right? But what if this whole sphere is like rotating about some axis? Right? Now, if it was pretty far away, you might be able to assume that the sphere is approximately a point and just do based on that. Right? But what if it's kind of close to the center? Right? Now, this distance, I'm going to call it H, just so I don't confuse it with any kind of R's. Right? Call it H, something like that. Right? So what parallel axis theorem says is that the rotational inertia about this big axis Maybe I should call this axis naught and axis 1, maybe something like that. The rotation about axis 1 is equal to the rotation about axis naught. I mean, if this thing's making 1 revolution per rotation, or something like that. Okay. Plus the mass of this object times h squared. Okay. Something like that. Okay. So you look up the table about, some textbook value. Like this could be, for example, 2/5 mr squared for just a solid sphere. Okay. And then you tag onto that the mh squared as if it's a single point for revolving around this other axis, like that. So I would be equal to that. Okay. That's parallel axis theorem. Okay. I don't think that's actually going to come up in any of the problems we do, but I want you guys to know about it. It's there. Might show up in college. If you guys ever become engineers or anything like that, physicists, they'll show up. Okay. All right. You guys good with that one? All right. And that's going to bring us to the last topic for today, which I'll at least get you guys started on, which is torque. Yeah, all my classes today, I'm starting to talk about this, plant some ideas, and then we'll talk about this tomorrow. Okay. So torque is represented with Greek letter tau. It's like a little curly T. Okay. And it has, well, there are a couple of formulas that go with this, but we'll start with this one, okay, which is R cross F. Okay. Notice I said cross. Now this is multiply. This is called a cross product. Oh, I need to draw you guys a picture. This one. What the heck am I talking about? Okay. My classic example is opening a door. So I got a doorknob, got some hinges over here. Hey, why is the doorknob opposite of the hinges? Because you guys feel this when you walk out, go to lunch in a few minutes. Okay? Because what if the doorknob was in the center of the door? Or even worse, what if it was really close to the hinges? How hard would it be to open that door? Oh, you have to apply a huge force to be like stuck here. But here, like no problem on the opposite side. Okay? So a little tiny force you can apply here and it opens the door, no problem. What's the deal with that? Because you're getting a lot of this, a lot of torque. Apply some force at this radial distance from the center. Okay. Now, I made this whole deal about a cross product, right? Because remember a few weeks back, you guys remember dot product? Like, for example, work was force times distance, right? But it was a dot product multiplication, right? Okay. Now, here's some ways to distinguish these things. Okay. Dot product, remember you multiply the parallel components together. Now, this cross product, what do you think you're multiplying? The what components? Not perpendicular, right? Imagine if it was parallel. Guys, what if you pulled in the same direction as the radial distance? Would that turn the door? No, that wouldn't do anything, right? Okay, so you need perpendicular. Hey, so perpendicular, do you think that'd be the magnitude of R times the magnitude of F times, remember dot product was cosine of theta between them. What do you think this one is? Not cosine of theta, sine of theta. Okay. And I want you guys to see why that's true. Because the way I've drawn this, see how there's like a 90-degree angle between the R and the F? Okay. Ooh, I bet that would maximize your torque, wouldn't it? If you push it at a 90-degree angle, wouldn't that maximize the torque? Because sine of 90 degrees is 1, like 100%. Okay. Versus, what if this angle went to 0 degrees to say you're pulling in the same direction as the width of the door? Okay. Yeah, you would have no torque at all, because sine of 0 is just 0. See how that's consistent? Yes, another thing with cross product, now this is a bit beyond the scope of AP, but this could show up in college, is that, you guys remember how multiplication has probably until today always been commutative? That's to say that A times B equals B times A, you can multiply in any order, right? Well, it's not true for cross product. Cross product, it's really important that you multiply in a certain order. Now, actually, this probably won't be an issue for AP style problems, but one way of solving cross products is with matrices. Did you guys do matrices in some math class? No? Yeah? Okay. Yeah. I'll show you guys matrices someday. AP doesn't really do them a whole lot, so I'll just anyway. Order does matter. If you do R cross F, then it actually ends up being a different type solution. What about the units for this? Units. Well, I see R is in meters, F is in newtons, and I remember doing the dot product. Force times distance was joules. So is this joules? No, this is not joules. Guess what this is measured in? Newton meters. And you just call it that. You always just call it Newton meters. Okay? So torque is measured in Newton meters. And nothing else. Don't ever say joules because it's a completely different concept. Okay? You know what else torque is equal to? I times alpha. Because this is sort of analogous to F equals ma. You guys remember how Newton's second law of motion, F equals ma, right? Okay. Torque is equal to I times alpha. Do you guys see the rotational equivalent analogous parts being plugged in there? Okay. This is sort of Newton's second law of motion, just in a rotational context. Or probably a better way to say this is alpha equals torque divided by I. But hey, and I, that's what we just talked about. That was all these notes. That's what I is, so some of them are squared. There's a table in the book. That whole deal. And alpha, that's like radians per second squared. Ooh, okay, so if you put a torque on something, wouldn't that cause it to like speed up or slow down spinning? Okay. Here's the last thing I'll leave you guys with today. Let's tie this all together. Suppose you've got a big solid disk, and it's rotating about the central axis, or could rotate about that axis. Hey, maybe kind of like the stern table. This could be the stern table. And you wind some string around it. And then you pull on the string with some tension. I'll call that force for tension. Okay? And I bet that string is always sort of definitionally pulling at a 90-degree angle to the radial size of that. Okay? And this disc has some associated rotational inertia. It's speeding up spinning because you're pulling it. Okay? How fast is it speeding up spinning? Isn't that like asking for alpha? Do you think you guys could say I times alpha is equal to R cross F? And since it's perpendicular, it could be like that. Could you guys solve for alpha if you knew those other three things? You guys see that? All right, so that will be our pause point right there. And let me know if you have any questions.